Welcome to Week 9, Lecture 1 of EBME401. This is the very last week of the signals portion of this course. And this week, we're going to turn from one-dimensional signals, which we've been talking about for the past 4 weeks, and we'll take a look at multidimensional signals, specifically images, as imaging is a very important part of biomedical engineering. So again, so far we've focused on signals which are functions of one independent variable, usually time. And we're denoting these one-dimensional functions as f of t. This is our continuous time signal. We also had f of n if we're talking about discrete signals. However, we can also have signals that are functions of more than one independent variable. For instance, we could have a two-dimensional signal that's a function of both time and position. So for instance, f of t and x. We could also imagine a two-dimensional signal where the two independent variables are spatial positions. So this would be f of x and y. We can also have higher dimensional signals, for instance this f of x, y, and t, which is a function of space in two directions and also a function of time. And we can go on and on with these multidimensional signals. For instance, we could have a 3D function of space, or a 3D function of space and then a function of time. This would be a 4D signal. So we're mostly going to focus on two-dimensional signals in the next couple of slides. But all of the things that we're going to talk about can be extended to higher dimensional signals. And of course, all of these signals here are denoted as continuous functions of time and space, but we can also have discrete functions of time and space. The multidimensional signals that we'll mostly focus on in the next slides are digital images. So digital images are discrete two-dimensional signals that we're going to describe as f of m and n, where m and n describe the indices of the pixels in each of the two directions. So let's take a look at a couple of terms that we're going to be using over and over again to describe these digital images or multidimensional signals. And we'll use the example of this nice cute cat here. Alright, so first of all, we talk about the field of view in the x and the y direction. The field of view in the x direction is FOVX, and the field of view in the y direction is FOVY. And these terms describe the extent of our image in the y or the x direction. And note that the extent can be different in these two directions, as these directions are completely independent. Our digital image will be made up of an array of pixels. Because this is a two-dimensional image, we're going to have a two-dimensional array of these pixels. And these pixels are going to describe the spatial resolution that we have, again, in the x and the y directions. The resolution in the x direction we're going to call delta x, and the resolution in the y direction we'll call delta y. And again, these two directions are completely independent. We can have one resolution in the x direction and a different resolution in the y direction. And both the resolution and the field of view terms have units of meters, or centimeters or millimeters, but these are units of length. We can describe the number of pixels that are contained in our image by taking the field of view in one direction and dividing it by the digital resolution. So the number of pixels we'll have in the y direction is the field of view in the y direction divided by delta y. And the number of pixels we have in the x direction is again the field of view in the x direction divided by the resolution in the x direction. And so the total number of pixels that we have in our image will be nx times ny. And again, the x and the y directions are completely independent here. We don't have to worry about affecting one direction if we change the other direction. So although we looked at this example of a cute cat on the previous image, we're really mostly interested in medical images. So medical images, as we've talked about before, can be two-dimensional signals, three-dimensional signals, 4D, etc. So for instance, a two-dimensional image could be a static image where we are looking at pixels in x and y directions. So this is exactly like our cute cat example, or this MRI image of the brain, which you see on the right-hand side. Our three-dimensional images, again, can be static images with x, y, and z directions. So here we have 3 spatial directions. Or they could be two-dimensional images, which we're looking at over time. So for instance, if we have a two-dimensional image of the heart beating, this would be an example of a 3D signal where 2 of those dimensions are spatial and 1 is temporal. And again, we can have 4-dimensional images where we have a 3D space, which changes over time. Or we could have a 3D space with additional spectral information, which tells us about chemical composition. But all of the dimensionality that we talked about for general signals can also be used for medical imaging. Because medical images are simply multidimensional signals, we can use a lot of the terms that we learned before to describe signals in order to understand properties of medical images. For instance, medical images are discrete functions of position and or time. And so we're not usually talking about continuous variables here, but instead discrete values that we can usually put in, for instance, a matrix which will make up our image. Medical images are band limited, meaning that they have a finite number of pixels in each direction. What's different about the information contained in medical images is that these pixel values can be either real or complex. So you'll recall that all of the time domain signals that we've looked at so far have just had real values. We only had to plot one axis when we looked at all of these time domain signals. However, medical images can have, for instance, a phase associated with each of the pixels. And so these complex values we would then have to represent, again, using either a real and an imaginary portion of the image, or a magnitude and a phase portion. And actually this phase information is very important, for instance, for magnetic resonance imaging. And so it's important to retain this information when we're looking at these images. The pixel values can either be integers or they can be floating point values. This just depends, again, on whether we've collected our raw data, where these pixels can usually take on any different value, or we're talking about specific medical imaging formats where our pixels are integer valued, and we'll look at that in just a bit. Also interesting is that the pixel values can either have units or they can be in arbitrary units. And again, this depends on the imaging modality that we're looking at. So in CT, for instance, each pixel has a unit which is known as the Hounsfield unit. This Hounsfield unit describes the attenuation that is experienced in each particular pixel. And so it's important to keep the scaling of these images the same so that we don't change these Hounsfield units. MRI, on the other hand, doesn't have any units associated with it. These are completely arbitrary, so we can take our entire two-dimensional signal and multiply it by a constant, and this won't actually change any of the information in our actual MR image. So it's important to know with the imaging modality that you're working with whether these pixels have units or not. Alright, so let's take again a look at how we depict some images, and we're again going to our cute cat because this is an example that everybody can kind of relate to. So when I looked at this image, I put it into MATLAB, and I saw that it had a size of 596 by 452 by 3 pixels. So actually, this part here is 452 pixels. The x-axis is the 596 pixels. And these 3 pixels describe 3 separate color channels: red, green, and blue. And so I can look at each of these color channels separately, or I can combine them all together in order to get this true color image. Unlike an actual photograph, though, we'll usually look at medical images with just one color channel. These are usually depicted in what is known as a grayscale. So here in MATLAB, I've taken my cute cat and I've simply added this third dimension up in order to get an overall pixel value, and then plotted that using my grayscale. So you can see that everywhere where this image is dark, this corresponds to a very low pixel value, and everywhere where the image is bright, the pixel value is high. And so you can think of the intensity of the image just corresponding to either a low or a high amplitude for that pixel value. So grayscale is just one of the many different color maps that we can use to represent our images. So sometimes we might want to represent our image using the jet color scale, for instance. So instead of going from black to white, we're going here from blue all the way up to dark red. It might be easier to see certain features in our image if we convert it to this color scale, but there's a ton of additional color scales. So this is just one example, this hot color scale, where again we're going from a dark red here to a really light yellow. And we're most commonly going to stick with our grayscale for the medical images, which you'll see again in future slides. As we talked about before, we can select different color maps for our different medical images, and we can also scale these images in order to bring out different features. So the example that I'm showing you here is an MRI image of the heart, and actually what you see here, this is the left ventricle, this is the right ventricle, and this here is the chest wall, and here are the lungs. Alright, so here we see that it's very difficult to appreciate different features of this image because the image is very dark. So actually what's happening here is that there's some fat on the left-hand side of the image that's taking up all of our intensity range. And so because this is an MRI image and it doesn't have units associated with it, we can choose to scale our image slightly differently to bring out different features in this image. So for instance here I've brightened the image simply by taking each pixel to a power less than 1. And here I find that this image in particular makes it a lot easier to see the different features. So it's the same image where I've just changed the scaling. And this is done very often by radiologists so that they can better see different features in our image. So we have to know though if it's possible to perform the scaling without changing the information content in our images. For a CT image, because there are units associated with each of these pixels, performing the sort of scaling isn't necessarily allowed. And so what I've actually done to make this particular image is that I've taken all of the pixels in this image and I've again simply raised them to the power of 1/2 in order to brighten up the image, to change my contrast a little. And what this is doing is making my bright pixels appear less intense in comparison to some of these darker pixels. We've also talked about using different color maps, and so actually this image here is equivalent to this image without changing the scaling, just using a different color map. And again, the features are a little bit easier to make out if I'm changing the color map. This red area is no longer taking up so much of the range of my pixel values. And of course we can switch this to color map hot, but we see here it's also a little bit more difficult to see. So I might want to stick with this color map jet, or else this scaled image here, if I'm looking to make out specific features in my images. I'd like to briefly go over some of the different notations that we use for orientation in medical imaging. So we're going to talk about 3 primary frames of reference. The first, shown on the left-hand side, is just the frame of reference of the bore of the scanner. So here we have a patient who's lying in, for instance, an MRI scanner, and we'll usually assign the Z direction to be the direction of the bore, so this direction here. And the X and the Y directions are 2 directions which are perpendicular to the bore. And we generally think about this as being the direction in real space. So this frame of reference is just going to describe, again, how our scanner is oriented in actual space. But this frame of reference doesn't really describe what's happening to the patient. And so we have another frame of reference which is in the patient orientation. So we'll talk about 3 separate directions. So there's the up-down direction, or superior-inferior direction. We have the left-right direction. And then we'll have the front-to-back direction, or anterior-posterior direction. And so again, this is going to describe how different parts of the patient are related to other parts of the patient. So for instance, we can say the head is superior to the feet. And this is how we're generally going to orient the images that we acquire with our medical imaging modalities. And so we can slice our patient in any of these 3 orientations, or maybe some combination going through 2 of the orientations. That would be an oblique slice, or even all 3 orientations. That would be called a double oblique slice. But we also have a 3rd frame of reference that we're typically going to be using when we talk about medical images. And this is the frame of reference of the image itself. So for instance, if we, cut a slice here directly through the patient's brain, and this was the image that we collected, we'd say we'd have a transverse slice here. And so our I direction here would correspond to a left-right direction. And this J direction would be anterior-posterior. If we had additional K direction here, we were doing 3-dimensional imaging, that would be in the superior-inferior direction. However, we could imagine, again, cutting through these different planes in the patient orientation. So we may not have exactly a slice going right through the patient's head, but it might be slightly tilted. And in that case, we're going to have a little bit of a different orientation in our actual image. And so usually we're going to keep these indices here, which just correspond to up and down and left and right in the actual image itself. And again, we have to understand exactly the geometry of how we've collected our image to see how this relates back to our patient frame of reference or even our scanner frame of reference. Let's just briefly look at the three common orientations for medical images. So these are the three that we saw in the center on the previous slide. So the first and the easiest to kind of picture is a transverse or an axial slice. So this was shown again on the previous slide. For instance, this would be cutting right through the patient's head. So here we see that we have the anterior part of the image here, the posterior part back here, and then the left-hand side of the patient's brain is on the right-hand side of the image, and the right-hand side of the brain is on the left-hand side of the image. This is because we imagine viewing this image as if the patient is lying on a bed, for instance, we're a doctor looking at our patient, and we're approaching the patient from their feet, moving towards their head. And so if you picture walking up to a patient who's lying on a bed in that way, their left-hand side would be on the doctor's right-hand side, which is why this left-hand side here is on our right-hand side. The next common orientation is what's known as a sagittal orientation. So here we have the superior direction and the inferior direction, and then anterior will be to the left and posterior will be here to the right. So this is like cutting the patient directly in half from the top of their head through the bottom of their feet. And this is pretty easy to see here in this head image. So you can see the patient's nose, and here's the back of their neck, for instance. The third orientation is what's known as a coronal orientation. So here we're again cutting our patient from the top of their head to the bottom of their feet, but in a direction that's perpendicular to the sagittal images. Right? So here again we have superior and inferior direction, the top of the head and the bottom of the feet. And again, as in our transverse and axial images, we have the right-hand side of the patient on the left-hand side of the image, and the left-hand side of the patient on the right-hand side of the image. And again, you could imagine that this image is in the orientation of a doctor approaching a patient from the front. So if I'm a doctor and I'm walking up to my patient, then their left hand will be on my right side and vice versa. So this is why we have this slightly unusual orientation when it comes to talking about medical images. But this is really important to remember which side is which. You know, we don't want to amputate the wrong hand or take out the wrong kidney, for instance. And so we have to keep these conventions so that we know which side of the patient we're talking about when we're looking at each of these medical images. So in order to keep all of these images standard, physicians generally use images in what's known as a DICOM format, where DICOM stands for Digital Imaging and Communications in Medicine. So these images will not only contain the actual image information, so for instance what we're seeing on the right-hand side here, again, our heart, but also information about exactly the field of view of this image, what the resolution is, exactly the orientation. So for instance, this is a double oblique image going through all three of the patient axes, and we need to know exactly how we've oriented this image so that we can understand what we're looking at exactly. It will also contain information about any scaling we've done in order to make features of the image a little bit more visible. And there's also information about the patient name, the scan date, the date of birth of the patient. So it's important to remember that when we're dealing with these images, we may have some information about the patient that we don't want to transmit to collaborators, for instance. And so all of our DICOMs generally have to be anonymized before we can hand them on to collaborators as biomedical engineers. Right? This information is important for the doctors to retain, but we don't want to be giving information out about the patient and their birth date. So we have to make sure we remove that whenever we share images. In DICOM format, all of the values of the pixels are unsigned integers from 0 to 2 to the 16 minus 1. So these are all integer values. They're no longer floating points here. And so whenever we look at these images, we have to make sure that we're scaling them properly so that we can really see the full dynamic range. Otherwise, we'll be missing some of the actual content of our image. So now that we've talked about our medical images as images, we can now start to think about them slightly differently. So here as multidimensional signals. So because our images are just simply digital signals, we can process them just as we would any other digital signal. The one very powerful thing that we can do is transform our image into the frequency domain using a multidimensional discrete Fourier transform. And in this way, we can look at the spectral information of our images. And we'll talk about that in the next couple of slides. We can also apply a linear filter in either space or the frequency domain in order to suppress noise or to bring out wanted features in our image. And we apply these linear filters, again, just as we would any other digital filter. They just now can have multiple dimensions. We can also apply some nonlinear filters. These usually we apply in space because we can't calculate their transfer function, and they allow us to look at different features of images, including texture. And there's a very interesting example of using a nonlinear filter on an image in the text that is associated with this week. In addition to these signal processing methods, we can also use image-specific operations to extract additional sorts of information. In the next lecture, we'll talk about edge detection and segmentation, which is what we'll use to isolate different regions of the image so that we can better understand the content in those sections. There's also a text portion on registration. So this is how we align two images in order to better compare information between those images. So let's take a look at how we convert our spatial image into the frequency domain using a multidimensional discrete Fourier transform. So you've already seen the discrete Fourier transform applied in one dimension, but we can also apply a DFT in multiple dimensions just by applying a 1D DFT in each direction separately. All right, so here we can convert our image, which we'll say is in the spatial domain, and we denote as f of m and n, into a frequency view of this image, which we'll denote as capital F of P and Q, where P and Q are our spatial frequencies. So we remember that m here runs from 1 to capital M, and small n runs from 1 to capital N. And when we convert our image into the spatial frequency domain, we have these new indices. So P will again run from 1 to capital M, and Q runs from 1 to capital N. And so it makes sense that we're converting a 2D image into a representation in the frequency domain, but we're not changing the dimensionality because we know that when we apply a DFT, we're not losing or adding information, right? So it makes sense that what's happening in this domain is the same as what's happening in that domain. It's just a different way of representing our information. So let's look at the mathematical expression for a 2D DFT and look at what it's doing. So here's our 2D DFT. So again, we see that we're taking our image and we're converting it into the frequency domain by applying these two exponential functions. All right, so we see first that this exponential function is going to link n, which is a function of space, to q, which is a spatial frequency. So here we're converting this dimension n into a spatial frequency dimension. And the second exponential is doing the same thing, connecting here this spatial variable m to the spatial frequency p by performing a 1D DFT. So actually, if we look very carefully at this equation, we see that this portion here is just a 1D DFT in the second dimension, and this portion here is a 1D DFT in the first dimension. So we're simply applying a 1D DFT along one dimension, followed by a 1D DFT along the other dimension to get our 2D DFT. And again, we can generalize this to any number of dimensions, but we're just going to focus here on 2D because it's a little bit easier to look at. So let's take another look at this 2D DFT. So the way that I like to think about it is that each dimension can be looked at as a series of 1D signals. So we can apply our 1D DFT to one direction of this series of 1D signals, and then to the other direction, or apply to the second direction and then the first. It doesn't really make a difference because in the end, as long as we apply a 1D DFT to each direction once, we'll end up with a 2D DFT. All right, so let's take a look at this in a picture. So here's my cute cat again, and I want to calculate the frequency spectrum of the information that's contained in this cute cat. So I'm going to look at this cute cat as a whole series of one-dimensional signals. Right? So each line here is just a 1D signal. So I'm going to compute the 1D DFT of each of these columns independently. And once I've done that, then I'll have a series of spectra which I've just aligned in a row, just like I have my image of the cute cat. So if I think about it, this line here, I took the 1D DFT and I've gotten one line here. And so we remember that red means that there's a high intensity and blue means a low intensity. And so here at the low frequencies, here is 0, we see that I have a high intensity in my 1D DFT, in my spectral information. And this is typically what we saw when we converted our images from the time domain to the frequency domain. We had a lot of energy right at the low frequencies, usually centered around 0, and less energy at the higher frequencies. Right? So this is exactly what we're seeing when we perform our 1D DFT. So then in order to do the second dimension, we simply apply another set of 1D DFTs, but this time in the other direction. All right, so we're going to think now of the center image as a series of rows, where each row is again a one-dimensional signal. And we're going to calculate the DFT of each of these 1D signals and put them all together in a matrix. When we do that, we end up with a full 2D DFT of our image. All right, so again, the very right-hand image is telling us our two-dimensional spectral content that was contained in our original image of the cute cat. All right, so let's think about this new space, because this is kind of a different way of looking at our images. All right, so we typically think about the image of our cat as simply being a two-dimensional image where each dimension has units of space. So we'll say our dimensions here are meters. So if we think back to all of the analysis that we did before of our time domain signals, we remember that we always had a signal of time, which we converted into a signal which was a function of frequency. So here, our time domain signal often had units of seconds, and our frequency domain had units of hertz, which is just 1 over seconds. And so performing the Fourier transform inverted our units. And we'll have exactly the same thing here after our two-dimensional DFT. So where before our image was in units of meters, our new space here will be in units of 1 over meters. So if we chose to use units of centimeters, for instance, for our image, then we would have units of 1 over centimeters in our new frequency space. Another way of thinking about this space, which we'll use later when we talk about magnetic resonance imaging, is that the space on the right-hand side has units of seconds. And in that case, our image will have units of 1 over seconds. So this may be a little confusing at this point, but again, it will come back to it in the text portion that talks about magnetic resonance imaging. So what do we call these new spaces? Well, we've always been calling the left-hand space the image, or the spatial domain, because we have two independent variables which represent space in this signal. And so when we talk about the right-hand domain, we can call this our spatial frequency domain. So this again goes back to this units of 1 over meters, where we're describing spatial frequencies. But we can also denote this space as an inverse space or a reciprocal space, and that's just kind of giving nod to the fact that we've inverted the units when we perform our Fourier transform. So you may hear reciprocal space or inverse space for this right-hand side representation. As I alluded to before, we can think about this right-hand side as having units of seconds, and this left-hand side as having units of 1 over seconds. And so if we use this sort of notation and units, then our right-hand space will be called the time domain, and the left-hand space will be called the frequency domain. So this is, again, a kind of backwards way of looking at it, which we'll use for magnetic resonance imaging, but I just want to bring it up now so that later on it doesn't become confusing. And what I'm typically going to call this right-hand space is the K space. So this is again related to the fact that we have spatial frequencies as our units. And so K space is a very common way of describing this multidimensional Fourier transformed space, which is looking at the frequency content. So from now on, I'm going to call the space K-space. So let's look at the properties of this new K-space. So again, we had our left-hand image, just the cute cat. We performed a 2D DFT, and the resulting space we're going to call K-space, which contains all of our frequency information. So very early in this presentation, we described the resolution in the x direction as delta x. But if we're thinking about our image as a signal, we can also describe the resolution in the x direction as our sampling interval, capital TS. And we know that our sampling interval is going to be related to our sampling frequency in our new K-space. All right, so the sampling frequency here, Fs, is going to describe the extent of our K-space in this Kx direction. So this is the x direction in K-space. So we can say that this point here is minus Fs over 2, and this point here is Fs over 2. And we're often going to call this, instead of Fs over 2, we'll call this K max, and we can call this side here minus K max. We can also think about the field of view in our image, which we before denoted as FOVX. And this, thinking again about our image in terms of a signal, is equivalent to the total acquisition period, T0. And we know that the total acquisition time is related to our spectral resolution in our new K-space. All right, so our T0 is inversely proportional to F0, where F0 is the spacing between our spectral points. And so because we're denoting this as spectral resolution, we often call it delta Kx here in the x direction. This is the resolution between our different spectral points. And again, here we're just talking about the x direction, but we'll have similar relationships between our y direction. But because the x and the y direction are independent, so are the kx and ky directions. We can have different values for spectral resolution in the kx and ky directions, or different values of the k-space extent in the x and the y directions. So again, just to summarize, we see that here our sampling interval Ts, which is equivalent to our delta x in the image domain, is equal to 1 over Fs, or in other words, 1 over 2 times K max. Our T0, which corresponds to the field of view, is inversely proportional to F0 here. This is our spectral resolution, so we often call this 1 over delta Kx. And if we take our field of view and we divide it by the resolution, so here we'll write this field of view x divided by delta x, we know this should give us the number of points in the x direction. And we can see that this is equivalent to Fs divided by F0, so the extent of our K-space divided by the spectral resolution, which will again be equal to Nx. So again, we have the same number of digital points in our image and in our K-space. All right, so again, let's summarize some of the properties of our images. These properties have the same relationships as our 1D signals, but we just have to think about them very carefully to understand the connection between the imaging properties and our signal properties. So first of all, for a given field of view, the smaller the delta x, the higher the resolution, the larger the K-space extent will be. All right, so let's think about this in terms of our signals again. So delta x corresponds to Ts, and Ts equals 1 over Fs. So here, if we had a very short sampling interval, then we'd have a very high sampling frequency. And conversely, if we had a very long sampling interval, Ts, then we'd have a very short sampling frequency. And so we see that this relationship here is exactly the same as the one that we've seen before, but we just have to think about this, in terms of signals in order to understand where it's coming from. Similarly, for a given spatial resolution delta x, a larger field of view will lead to a smaller spacing between our spatial frequency entries, so a higher spectral resolution. And again, we can relate this back to what we know about signals. So a field of view in signals terms is just our T0, and T0 is inversely proportional to F0, which was our spectral resolution. And so what we're saying here is that if we have a large field of view, then we'll have a high spectral frequency resolution. We'll have a smaller spacing between points in our K-space. So again, this makes sense if we think about it in terms of the signals perspective, but it always helps, if you're starting to get confused, to go back to our signals relationships and think about what those mean in terms of our images. So let's take a look at an example where we're examining different portions of our spectral content in order to understand how that relates back to our images. All right, so we're starting here just with our image. It's our normal cute cat, and we performed a 2D DFT, and we have our K-space now on the right-hand side. So the first thing I'm going to do is just to cut out the very center frequencies here. So if we assume that this is 0, and this is minus Fs in the y direction over 2, and this is Fs in the y direction over 2. And again, we have here in the x direction our 0 frequency. This is minus Fsx over 2, and here we have Fsx over 2. Then essentially what I'm doing is I'm cutting out the very low frequency information from my K-space. I'm discarding all of the high frequency information. I'll get rid of these so we have more space. Okay, so when I extract this low frequency information and put this right here, and I perform a 2D DFT to get to an image, what I see is that I've lost a lot of the resolution in my image. All right, so this is actually really interesting. So what I've done is I've reduced my Fs, and we know that Fs is inversely proportional to Ts, which we've said corresponds to my delta x. So by reducing my Fs, I'm increasing my Ts and increasing the spacing between points in the image. So here I end up having bigger pixels because my delta x has increased. So I'm losing spatial resolution if I just focus in on this very center of my K-space. So what if I now take the very center of my K-space and I leave it in a large matrix, but I turn all of these outer portions here to 0. I just get rid of all of those outer portions of my K-space. So this is equivalent to 0 padding, right? I only collected the low frequency information, and I'm 0 padding now all of this high frequency information. So I'm going to just 0 pad here, and there's all my 0 padded data. And if I then take this new K-space and perform a 2D DFT, we see that I now have an artificially increased resolution. I'm basically interpolating between the points I have in this image in order to get this image down here, right? This is just a 0 padded data set. And we know that 0 padding isn't actually going to increase the resolution, it's just going to interpolate between points. And again, this is exactly what I see happening in my image, that I still have the same delta x, the same resolution that I had in the image right above, but I've now interpolated between my points. So again, these relationships are no different than the ones that we've seen in all previous one-dimensional signals. It's just a little bit tricky to think about my images as signals in the same way, using different terminology. But whenever it gets confusing, I find it easier just to go from, for instance, a delta x to a Ts, and then recalculate all my relationships, and then think about what that means either for the K-space or for the images. So in all the text portions, there's going to be some examples of how we can filter our images. So again, just perform the same digital filtering operations that we did from our one-dimensional signals. And you'll also look at some very specific imaging examples that we can do now because we're talking about multidimensional signals as opposed to just one-dimensional signals. So thanks a lot.